Greetings. I'm very pleased to talk to you today about some work that we've been doing at George Mason University on ultrasound-mediated ionic modulation in the brain. This work was done by my graduate student, Monica Gertz, in collaboration with Parag Chitnis. So the work that I'll be talking about today is computational work based on experimental results that Monica produced from experiments in rat hippocampus, where she used focused ultrasound to stimulate the CA1 region while measuring the potassium extrusion in that region, as well as the oxygen consumption in that region. She also stimulated with electrical stimulation in order to compare to the ultrasound stimulation. These experiments were done using a 35 megahertz center frequency transducer. The individual pulses were 700 kilocycles, so approximately 20 milliseconds, repeated at a 10 hertz repetition rate. The experiments were performed in an epifluorescence scope, where the transducer was placed below, as can be seen in the figure. So the results are as such. You see in the top panel, very large potassium extrusion rates for neuronal systems. 30 plus millimolar is very high. And the oxygen consumption, about 2 milligrams per milliliter for every stimulation, you'll see compared to electrical stimulation is about the same. All right, so in order to replicate these results, we came up with a computational model based primarily on the acoustic radiation force. So in vivo, we'd expect to have some compression region and some expansion region, but for slice work, we'd expect to only see compression. So the model is based primarily on the compressive effects. And so what we see is that as the tissue is compressed, the solution outside of the tissue in the extracellular space can move around. That solution is composed of water and then solutes like sodium, potassium, chloride, and calcium. Some ionic composition is immobile, however. And so as the fluid is pushed out, the concentration of those immobile ions becomes quite high. And that can cause the flow of water back into that space, causing ultimately a dilution of the other ions. So the sodium, potassium, chloride, and calcium become less concentrated due to that osmotic flow. And those changes in ionic constituents lead to a depolarization of the transmembrane potential, and ultimately to the stimulation that we see. So here's a comparison between the results that we get from our model in the lower panels and the experimental results in the top. In both cases, we see a very large potassium extrusion, 15 millimolar approximately, and we see that in the initial stages, there's a small dip that occurs in the potassium that's seen both in the model and in the experiment. And then as the stimulation occurs, we see these what look like artifacts, but turn out to be actual effects in the model as well. And then we see in both cases this prolonged effect that happens after the end of the stimulation. Now, if we compare the metabolic demands of the electrical stimulation versus the FUS stimulation, we see that even though the potassium is much, much higher, 30 millimolar or in excess of 30 millimolar, compared to only a millimolar or so for the electrical stimulation, the oxygen consumption is similar, if not more, for the electrical, where every stimulation gives approximately 2 milligram per milliliter of depletion of oxygen for both FUS and for the electrical stimulation. And that same type of behavior is seen in the model. And another effect that we see is that the recovery is much slower for the electrical stimulation than it is for the FUS stimulation. And we can understand that from the model. We can see that what happens is in the compressed state, the transmembrane currents have a much larger effect on the concentrations outside. And therefore the potassium has a very high increase in its concentration, whereas for the electrical, it's quite moderate. And on the other hand, inside the cells, which are not becoming as compressed, we do not see the accumulation of sodium, as you can see in the lower panel, for the neuronal cells. The middle panel is for the glial cells, and there's a story there to talk about, but I do not have time. So for the lower panel, we see that the accumulation of sodium is much, much higher for electrical, even though the potassium is much smaller. And that leads to, due to the fact that the oxygen consumption is driven by the ATP consumption, which is driven by the sodium potassium pump, which is sensitive to both the extracellular potassium and the intracellular sodium. So in the time that I have, I've been able to show you that we created a model that is able to replicate the responses of potassium and oxygen to FUS and electrical stimulation. And we've been able to see that the mechanism for the acoustic stimulation is a combination of the compression due to ARF and the immobile osmotic agents in the surrounding extracellular space. And finally, we're able to explain why we see much higher metabolic demand in electrical stimulation than we do for the FUS stimulation. Thank you for your time, and I look forward to talking to you in the future.